I'll be talking about practical secure machine learning. So let me begin by describing a few scenarios from the space of secure machine learning that I will be focusing on today. The first one is that of secure inference or secure deployment of machine learning. It's a two-party scenario, and here there are two entities. Let's say the entity on the left has some pre-trained machine learning model which it wants to use, which it wants to provide as a service. So it has spent a lot of time, energy, money to train this very good model. So it's its intellectual property. And here in particular, we consider the weights of the model as being sensitive, or in today's LLM era, it can be a public model, but the carefully crafted prompt to this model is the intellectual property of the startup who came up with it. On the other hand, we have a user or a model consumer with sensitive inputs. It can be a user or a hospital with private patient data, and they want to learn the inference based on their sensitive inputs. So the scenario is that you have two entities, each have their sensitive inputs, and they want to collaborate. So the question is, can these two parties do private collaboration or secure inference without revealing the model weights or the input to each other or to anyone else? Okay, and today we are witnessing a rat race between large language models where each and every one of the startups or enterprises is claiming to have the latest and the greatest machine learning model for various tasks. And these claims are of high economic value, and big business decisions are made based on these claims. But how do you validate any of these claims? There are two problems. The first problem is paucity of good benchmarks. By benchmark, I mean inputs which have labeled inputs and outputs so that you can test the accuracy of the model. And since these models are expected to work in wide range of domains, it is very difficult to come up with good benchmarks in a domain-specific manner. So in like with paucity of good benchmarks, which like what happens is that each of these models gets evaluated on their own benchmarks, and sometimes these benchmarks are smartly crafted to show good accuracy. The second problem is that there's no guarantee that even when the public benchmarks are available, that the model has not seen these benchmarks or some form of it during the training process itself. And this is called contamination of the model with the test data. And with contamination, it is clear that the only way to avoid contamination is to keep the benchmarks private. Inspired by this is my second scenario of private benchmarking, which allows benchmarking of proprietary models on private datasets without revealing the model weights or the benchmarks to each other. So to address or to inspire this, let's say there is a hospital who wants to use machine learning for its patients. But before it commits monetarily to any ML provider, it wants to make sure that the model has good accuracy on its kind of patient data. And for this, let's say it has a small amount of patient data which is labeled and can be used as test data for this testing. However, this test data cannot be given to the model publisher to avoid contamination. The third scenario is that of secure training on joint data. So machine learning is extremely important and data-hungry application, and models get better with more data and more diverse data. So here there are two entities who want to train a model jointly on all their data, as if all the data was present together and you want to do centralized training. I'm not talking about something like federated learning, which keeps data separate. However, the issue is that data is often protected and cannot cross trust boundaries. This can be due to legal reasons, IP reasons, and so on. So the question is, can these two entities train a joint model on all the data put together without sharing the data with each other? Okay. So all of these three scenarios, be it inferencing, benchmarking, or training, can be trivially solved if you indeed had a trusted third party which was trusted by everyone or which lies in the trust boundary of all the data owners. Then what you can do is you can just send the data to this trusted third party who can do the computation and send back the computation results. However, in real scenarios, such an entity who's trusted by everyone does not exist. So the question is, can this trust in other entities be completely avoided? Can we do data collaboration without trusting or sharing the data with anyone else? And this is exactly what MPC enables. It looks magical at first, but what MPC enables is that it allows any collection of parties with sensitive inputs to compute any public function of their choice with strong correctness guarantees and cryptographic security guarantees. Correctness says that at the end of the interactive protocol, parties learn the correct output, and security says that parties learn only the output and output alone and nothing about the other party's input beyond what is revealed by the output itself. And it's clear that all the scenarios, inferencing, benchmarking, or training are special cases of MPC. Okay, so now that MPC is so great, What are some of the challenges in practical deployments or widespread adoption of MPC, especially for the case of secure machine learning? And there are three broad challenges. The first one is usability or programmability of these MPC protocols by ML practitioners who are largely MPC unaware. These ML practitioners only want to write the machine learning model in some high level framework like PyTorch or TensorFlow and do not care about how MPC actually works. So we want to design a toolchain which can take these high level model descriptions and automatically compile them to efficient MPC protocols for all kinds of tasks like training or inference. And ideally, we want to use these ML models as is without making any change to them to avoid the task of retraining, which you have to do to regain lost accuracy if you change the machine learning. Second is scalability. So we want our tool to support latest and the greatest of machine learning models out there. So the ML models are getting large and large every day. Healthcare models are large. Transformers are even larger. Transformers today have billions of parameters and trillions of operations, and we want to support all of these. The last is performance. By performance, I mean the end-to-end latency of secure implementations done via MPC. So earlier MPC protocols communicate terabytes or even petabytes of data for real-world ML models. And this just results in long run times for secure implementations. Moreover, while the ClearText benefits significantly from GPU acceleration, since the MPC protocols are bottlenecked by communication, they can't benefit much from hardware acceleration as well. Okay, in this talk, I'll tell you about EasyPeasy, which is the end-to-end cryptographic system for practical secure two-party machine learning, where we address all of these challenges and run real-world ML models. So to give a highlight of results, let's say we are working with CNN, which is convolutional neural networks, and the task of training. Then for training, like Piranha is the prior best state of the art, which does GPU accelerated two-party secure computation in the pre-processing model. I'll define this shortly. But to train a model for CIFAR-10 dataset, Piranha takes 19 hours and communicates 64 terabytes of data. Whereas with Orca, which is our work, we can do the same task in just 45 minutes and communicating only 0.66 terabytes of data. So we are 26 times faster and 99 times slower in communication. Next, coming to secure inference, here the prior state of the art is Meta's Scriptin framework, which can support large models. This is also GPU accelerated two-party secure computation in the pre-processing model. To do an inference of VG16 model for imaginary dataset, which is a 1000 class classification, Scriptin takes 13 seconds and communicates 16 GB of data. And with Orca, we can do the same task in just 0.5 seconds, communicating 0.32 GB of data. Now, later in my talk, I'll talk about transformers, but here's a highlight. We can do secure GPT-2 or BERT inference in just 1.8 seconds, which is almost real time, where Scriptin takes 20 seconds. We can scale to even larger models like Meta's Llama 2 with 7 billion parameters or 14 billion parameters and do inference in 27 seconds, whereas the prior tool Scriptin goes out of memory and crashes and hence has scalability problems as well. Okay, here's the outline of the rest of my talk. I'll start with the computation model, then some cryptographic protocols. I'll touch briefly upon transformers and end with a case study. Okay, so let's start with the computation model. So here we have our two entities, model publisher and model consumer. At the beginning, what happens is that there is a cloud provider which acts as an enabler of secure inference and acts as a dealer. What it does is it gives something known as correlated randomness to the two parties and sets up two machines with pre-filled randomness. This randomness only depends on the model architecture and does not depend on the sensitive model weights or the inputs to this model. Once this happens, the dealer goes away. And now these two parties bring in the sensitive inputs, which is the weights of the model and the inputs to the model, and run the secure two-party computation protocol with the help of the correlated randomness given in the pre-processing phase. This is the same computation model used by our baselines, which is Metascriptin and Piranha. To abstract it out, the overall protocol has two phases, an offline phase and an online phase. In the offline or pre-processing phase, there's a dealer which, depending on the function, gives the randomness R0 and R1 to the two parties and goes away. In the online phase, party uses randomness and the inputs to compute the function running the protocol. Our goal in this setting is to minimize the online latency and communication. And in the threat model, we assume that one of the two parties can be simonis corrupted. Okay, now coming to cryptographic protocols. So be it inferencing, benchmarking, or training, here's a list of operations we need to support for machine learning. First, we have the arithmetic operations like additions, multiplication, matrix multiplication, convolutions, and so on. All of these can be very efficiently realized using Weaver triple based preprocessing material, and in fact, they are very efficient. The online cost is only 2x the cost of the latest computation. Then we have a bunch of Boolean operations like truncations or right shift operations. ReLU, which is computing max of x and 0. There's max pool, there's average pool, and then there are very complex nonlinear functions like sigmoid, softmax, GELU, and so on, or something else like SILU in your transformers. Now, all of these functions are the bulk of the cost of secure machine learning. And there are various options to realize these functions in the preprocessing model. The first one is garbled circuits. Then you can do secret sharing based protocols or GMW. And the third option is to do function secret sharing based protocols. And my talk today will focus on our work using function secret sharing based protocols. So what is FSS or function secret sharing? It allows a dealer to split a function f into two parts, f0 and f1. Now these function shares can be evaluated on a public input x to give f0 of x and f1 of x such that these add up to f of x. This is completely non-interactive and you only need to interact to reconstruct the final output. So if FSS exists for a function, you have very low communication, but your function keys, which is f0 and f1, can be large, and the compute on these function keys can also be large. These f0 and f1 are known as the FSS keys, and the security property says that like either of these function keys, fb, hides the function f. So these f0 and FSS can be used to hide secrets within the function, which we will crucially use later. Okay. So here I'll give a brief overview of how we can use this FSS to construct two PC protocols. Let's say you have a circuit with 3 gates F, G, and H, where each of the wires carry ring elements. Then what you do is, let's say you take the gate F, which goes from input X to output Y, which are ring elements. You transform this function into an offset gate, which instead of taking inputs and outputs, it takes masked inputs and produces masked outputs. By masked input, I mean X plus R, where R is a random mask unknown to the parties. And it gives y hat, which is y plus s. So f hat in particular computes f on x hat minus r plus s. Now we think of these r and s as secrets embedded within the function f hat, and we rely on security of FSS to hide these secrets. Now security crucially relies on the fact that these masks are unknown to the evaluating parties. So now, given this transformation, you do this transformation on gate by gate for the whole circuit, and you go from circuit to offset circuit, where each gate now goes from masked inputs to masked outputs, and each wire has a freshly chosen mask. So now, this is what happens in the 2PC with preprocessing model. The dealer gives out function keys for f hat, which is f hat 0 and f hat 1. And in the online phase, parties will have x plus r, which is known to both parties, where r is unknown to both the parties. They compute these function shares to learn the secret shares of y plus s. They will interact in one round of interaction to reconstruct y plus s, which is a masked output, and continue to evaluate the next gate and so on. So the bottom line is that to compute each gate for which FSS exists for the offset gate, you only need to communicate one ring element in one round, and that's it. Okay. So in this slide, I want to compare the complexities of FSS-based 2PC with preprocessing with other approaches like garbled circuits and GMW, along the parameters like online communication, online rounds, correlation size or the size of the preprocessing per party, and computation. And here, as an example, I have picked ReLU circuit, which is max of x and 0, where let's say x is some n-bit input, and lambda is a computational security parameter, typically 128. So if you look at garbled circuits, they have high online communication even in the preprocessing model because the input labels need to be transferred in the online phase. So you have at least lambda n online communication. Online rounds are good, it's only 2. The correlation size is also large because the garbled circuit needs to have a ciphertext per AND gate. And the computation is also large because you need to do a bunch of PRF computations per AND gate. GMW, on the other hand, has low to moderate online communication depending on the number of AND gates. You need to communicate 4 bits per AND gate. Online rounds can be low to moderate depending on the depth of the circuit in the AND circuit. Correlation size is also low to moderate. You need to store a few constant number of bits per AND gate. But on the other hand, this computation is very fast. It's information theoretic. FSS, finally, has very low online communication. It's lowest of all. It's only 2n bits of communication because you only need to reconstruct the output. Rounds is just 1 because it's simultaneous message from both parties. Correlation size can be very high. It is n times lambda plus 2n. And the computation is also high because you need to do a bunch of BRF calls. So if you look at the online metrics alone, then FSS is highly appealing. It's not bottlenecked by communication, whereas it bottlenecks our computation and correlation size. Okay, now let's shift gears a bit and try to understand the bottlenecks or the prior state of the art in secure machine learning. So here we look at Piranha and look at one secure training iteration in Piranha for this network for CIFAR 10. And we observe that 85% of the time goes in communication. So if you need to increase performance, you need to bring down communication. And FSS is great for this. Okay, so let's look at the cost profile for FSS in 2PC. The state of the art on FSS prior to our work, they uses CPUs. And for tasks like training, there are three paths to the protocol. There's key read, computation, and communication. So the issue is, since the correlation size can be large, and for tasks like training, which has many iterations of secure computation, this correlation will not fit in the CPU memory and will lie in the disk. So you need to read this correlation from disk to memory, then do computation, and so on. The computation just refers to the online computation once you have keys in memory, and communication is the communication required. So as you can see, bulk of the cost is compute. Key read is also high, but it's not large enough that it can be hidden. So the key read for the next iteration can be hidden behind the computation of the current iteration. So it doesn't lie on the critical path. So we need to reduce compute. And for this, we use GPUs. It's easier said than done, and accelerating FSS on GPUs requires a bunch of system optimizations and also redesign of FSS protocols, which I will talk about. Okay. So believe me when I say that the bulk of FSS computation for Boolean operations is nothing but just computing many comparisons using something known as DCFs. What's a DCF? So let's say there's a function f parameterized by alpha and beta. This function outputs beta if x is less than alpha and 0 otherwise. It's just doing comparisons with alpha and outputting the special value beta, which is just typically 1. Okay. Now the key size for this function for n bits input and l bit outputs is n times lambda plus L. That is, depends on both the input bit length and the output bit length. And the online computation consists of 2n AES calls. So to accelerate compute, we need to accelerate AES on GPUs. So how do we do this? So while CPUs have intrinsics for AES, GPUs don't. On the other hand, GPUs have many threads which can compute many AES operations in parallel in theory. But if you do things naively, you don't get any speed up. And the reason is something called bank conflicts. So you need to do system optimizations to avoid these bank conflicts. You need to reorganize your data so that you're cache friendly on GPUs. So like GPUs have many very small cache which is shared across all the threads. So if you do things dumbly, then your cache locality will not be there. And moreover, you need to do packing efficiently on the GPU itself so that you don't have memory bloat and have less data going between CPU and GPU on the PCI bus. Okay, so once we do all this, without getting into the details, we have an FSS implementation on GPUs which is 20x faster than FSS on CPUs. Okay, now let's go back to the cost profile. We have the same three phases: key read, computation, and communication. Now computation is much smaller and key read and communication are same as before. But now here's the problem. Now key read can no longer be hidden behind computation, and we have a new bottleneck, which is key read. So to reduce this bottleneck, we need to design our FSS protocols to have lower key size. So what we do is we design better protocols which have lower key size and marginally higher communication so that end to end we have much better performance. To just give an example, for ResNet 18, we have almost 5x reduction in key size over the prior works. Okay, now quickly going over evaluation. Here we compare Orca with prior works, Piranha and Crypten, which are both on GPU and use secret sharing based approaches. We also compare with Llama, which is a prior FSS work but uses CPUs. So we have great speed ups and reduced communication compared to Piranha and Crypten across different benchmarks. Compared to Llama, which is the FSS on CPU, we have 100x speed up, which is coming both from GPU acceleration as well as key size reduction. But we have slightly more communication because the protocols trade off lower key size for marginal increase in communication. Okay. Oh, sorry. Okay, in the next part of my talk, I'll briefly touch upon transformers. So at a high level, transformer architecture looks something like this. It has linear layers and green boxes, which are just matrix multiplications, which are again very efficient. We don't have to worry about them. Then there are nonlinearities like softmax, GELU, layer norm, and so on, which are much more complex than things like ReLU and maxpool, which is a single comparison. And these nonlinearities, if you just look at it, looks like these. So GELU is this complex function which I don't even know how to compute. Softmax has exponentials and division. Layer norm has inverse square root, and so on. So not only are these complex, transformers have these in abundance. For example, in GPT-NEO, there are 25 million GELUs, and Krypton spends 20 seconds in computing GELUs alone. There are 49,000 softmax, and 16 seconds are just spent in computing softmax. So to speed up things on transformers, we need much better way to compute these nonlinearities, which also need to be precise to preserve model accuracy. So I'll show you what we do for GELU at a very, very high level. So here's a graphical representation of GELU. If you stare at it closely, it's very close to a function we all know, which is ReLU, which is just max of x and 0. So like ReLU is 0 for negative x and x for positive x. So we define this function delta x, which is ReLU minus GELU, and GELU is just ReLU minus delta x. Now we know how to do ReLU from Orca. It's easy to compute. It requires two DCF evaluations. But what about delta? How do we do this? So this is how delta looks like. It's a highly nonlinear function. There's no good approximation for delta. The first thing which comes to mind is let's use the lookup table and just look up the value of delta from a lookup table. But here's a problem. To preserve accuracy of transformers, x comes from a large domain. It has 50 bit length, let's say. Then to compute this like lookup table securely, you'll do at least 2 to the power 44 AES calls per input. This is huge and you cannot do this. So we need to come up with a small lookup table to do this efficiently. So how do we do this? We stare at this function, and the first observation is obvious that delta x is 0 outside minus 4 and 4. So the first thing we do is we clip x to lie between minus 4 and 4. Next, we observe that delta x is even. So we compute y, which is the absolute value of x. So it reduces the LUT size further by half. And then we say that x is a fractional number. It has some integer bits and some fractional bits. In our case, f had 12 bits of fractional parts. We realize that not all 12 bits are critical for looking up a precise enough value of delta x. So we get rid of few bits and retain 6 bits of precision in x. So we call this z, where we truncate x by 6 like lower bits. And we're left with z, which lies between 0 and 4 now, and has 6 bits of fractional parts. So z has total of 8 bits. And we can have a lookup table with 8 bits. Okay. So we now need to realize this like approximation securely. So 8-bit like LUT is cheap, but we need to reduce the cost of other functions. So we need to reduce the size of comparisons used. We also need to reuse the comparison results and so on to overall bring down the cost of GELU. Okay, so I'll not have time to go over these. I urge you to look at the paper for these details and also our approximations for softmax and layer norm. But what I like to emphasize is that the approximations which we use in our work sigma for these nonlinearities are very precise, and they're precise enough that we do not need to do any retraining of the transformer, and it matches the accuracy of PyTorch, which works over floating point. We can just take floating point pre-trained weights as is and run it through sigma. And here are the performance numbers, like comparing with Krypton on wide range of transformers, starting from BERT tiny to BERT large, the GPT models, and the largest model, which is Llama 2 by Meta, on like 7 billion parameters and 13 billion parameters. We are faster than Krypton all over the board, and on the larger models, which is Llama 2, Krypton crashes with out-of-memory error, and Sigma scales gracefully. Okay. So far, I only talked about Simona security, where the parties are expected to follow the protocol faithfully. What about malicious security? So here again, we have a choice between GMW and FSS. In the Simona's case, we saw that like GMW has lower correlation size, but has much larger compute and rounds. In the malicious case, this win also goes away, and the correlations are also much larger, because now you need authentication on each of the triples, which is much larger, at least 40 bits on each bit. Okay. So here we realize that if you do things well with FSS and carefully redesign your protocols, then FSS can win on all parameters. It can have lower correlation size, lower communication, and lower rounds. Our starting point here is just speech style authentication, where we change our FSS scheme to now output, instead of just like simple shares, to now output authenticated shares. And we can combine them together with like gate by gate and get the protocol. But you can do much better. You can redesign these FSS protocols based on the ideas in Orca and Sigma to get much lower key size and communication. Okay, this is an ongoing work which I'll let you know about soon. Okay, finally, I'll move to the case studies. It's a quick thing. So, what we are realizing today is that there are two kinds of contamination of LLM which are being talked about today. The first is, how can I guarantee that my inference queries are not being used to fine tune the LLM model? This is called contamination of the LLM with sensitive inference queries. And here, secure inference provides a very neat and clean solution to the problem, that it does not leak the inference queries to the model, and our work like Sigma enables this. The second contamination is the one I talked about before, which is, how can I guarantee that model has not already seen the test data? That is, the model has not been trained on and contaminated by some form of or the other of the test data, and especially given the fact that LLMs today are seeming to be trained on whole of internet today. And the only solution here is to keep the benchmarks private and do private benchmarking. And inspired by this, we built TRUCE, which stands for Trusted Uncontaminated Evaluation, which is a platform for evaluating proprietary models on private benchmarks. It enables creation of a public leaderboard comparing accuracies of different models on consistent set of benchmarks and supports LLMs as well. And this framework is open source on GitHub. Finally, I would like to conclude by saying that PPM is a highly impactful research area with lots of natural security questions. And MPC is a perfect fit for many of these for things like inference, benchmarking, and training. And EasyPeasy provides a state-of-the-art performance protocols and a usable programmable toolchain for many of these models like CNNs and LLMs and more. And lastly, I urge you to try out EasyPeasy. All our code is open source on GitHub. And if you hit into any issues, please don't feel shy to write to us at easypeasy@microsoft.com. Thank you. Questions?
Questions?
Probably has been said, but I didn't hear it. How many digits of precision you have compared whatever model you have with an unencrypted one?
Sorry, what?
How many digits of precision your framework has with an unencrypted one, running the exactly same model?
So the ClearText model uses floating point, which is 32-bit floating point, and we use roughly like 50 bits total, which is like 12 bits of fractional part and rest in the integer part.
Right. So how many parts are the precision? And I mean,
12 bits of precision.
Okay, so you're getting exactly the same 12 bits of precision running the unencrypted model vs your framework.
So like when we compare the accuracy of the unencrypted model, we just use plain like PyTorch in floating point, whereas MPC uses something known as fixed point arithmetic, where
Right.
you have 12 bits of precision.
Okay.
Yeah, thanks for a really nice talk. I'm just curious how much of the GPU optimization is specific to, let's say, FSS versus MPC versus general crypto?
You mean FSS versus secret sharing, let's say?
Yeah, like how generalizable are the optimizations?
Not very, I would say. So if you look at the FSS cost profile, FSS is really compute bound, whereas if you look at the secret sharing based approaches like GMW, they are all communication bound. So like Piranha and Krypton did use GPUs for accelerating secret sharing based protocols. I don't like, if you ask me, I was very surprised to see that they got any benefits, because those protocols, if done well in implementation, should actually be bottlenecked by communication, and you should not see any benefits of using any acceleration. So it really depends on the protocol, whether you're compute bound or communication bound.
I see. Thanks. Any other?
So like for example, FHE would benefit greatly from GPUs or any kind of like custom hardware, because FHE is also compute bound. But then it doesn't do AES, it does a bunch of tensor operations and so on. So the kind of tricks which will go there will be very different. But the general flavor, like doing memory optimizations, etc., would be very useful. But not AES in particular.
Thanks.
Any other questions?
So is it possible to combine Elite's work with yours, like to get this pre-processing for life? Because both are
discussion for dinner today. Today. We'll let you know tomorrow.
Okay. Thanks.
Okay, thank you. Let's have a huge round of applause. Right, so we will now be breaking for lunch and we will reconvene